Welcome back, everybody. It's lecture 12. Boy, the year is passing quickly. Today, we are going to continue talking about feed-forward networks. Again, this references chapter 14 in the textbook. And we'll see how far we get. I have a series of exercises, some of which are pretty quick. I may use the breakout rooms and break people up into small subgroups. And instead of having everybody do every sub-exercise, I may ask people to work on different sub-exercises and then come back together to present quickly their results. Be a little bit more efficient. I'm going to come back to this question of how do you interpret networks. We've gone over those slides a couple of times, but I think they're important enough. It's worth doing it again. And then we will begin to dig into the feed-forward network analysis from that chapter 14. So last time we talked about using that colon equals syntax to do continually updated values in antimony and some of the slight strangeness that gives rise to. For example, if something is defined with a colon equals, you can't reassign it in Python. So that's an issue. But it does allow us to do things that can be convenient with things like scaling, time or value dependent functions, and so on. And we do have to be aware of that when we write code. Joel and I ran into a situation the other day in Python where we were saying, boy, Python really should have separate equal signs for assigned by value and assigned by reference. Because depending on what's on the right-hand side of the equal sign, sometimes it makes the objects the same, and sometimes it passes the value. And if you read in the literature, it will tell you when those two things occur, but it would really be nice to actually have a separate equal sign so you knew always which one it was from looking at the code, rather than having to see what kind of object it was. At least antimony is good that way. You have explicit difference. And we talked a little bit about using the prime to indicate time derivative. And just a reminder, when you use that, you have to give the initial value. So coming back to the feed-forward networks, we asked the simplest possible feed-forward network, which is that P1 is a species that acts on P3 both directly and indirectly. And we're going to think about these as regulatory interactions. And so each of those interactions could be either activating or inhibiting. And so in principle, there are three links, each one of which could be activating or inhibiting. So there are 8 possible combinations. And there is this interesting question, which is why would you either have 2 pathways that do the same thing, which is called a coherent network, or 2 pathways that do opposite things, opposing things, which is called an incoherent network. And we could ask a lot of questions about these. How does the level of P3 change as the equilibrium as a function of P1 is the obvious one. How does it depend on the parameters? But these kinds of networks typically have particular temporal behaviors. And so looking at the steady states is not usually enough to really understand what they're doing. Something that we haven't really gone into, although we could do quite quickly in antimony, is do stochastic simulations. We haven't covered it, but you could do a stochastic simulation by replacing the word simulate with Gillespie when you invoke the simulator. And you can then see how these systems respond to noise. It winds up that feed-forward networks have rather different noise dependence from the single network, the single function equivalent. And so we're going to always follow these same steps. first we'll look at the steady states. Then we'll ask how does the temporal behavior of each of the components work, and then what happens when we combine the two paths. So you've seen these slides before. Again, one of the things that we have to learn is a language, and I think when you learn a language, repetition is essential. That's why we're covering this multiple times, is that very often you'll see a diagram that looks like P1 here activates P2, and we want to turn that into mathematics. And if there's one thing, I guess, that functionally, procedurally, that I hope people walk away from this class with, it's that when you see a diagram like P1 activates P2, you immediately think, oh, I know what that looks like mathematically. If we're going to learn one functional thing, that would be it. And so we remember that P1 activates P2 implies P1 somehow turns on transcription of a gene, which then produces a protein. Mathematically, that means that nothing goes to the protein at a rate that depends on the level of the gene. Whenever we have transcription to translation in a diagram like that, it's implied that the protein decays. If it doesn't, we wind up with an infinite amount of it. And so actually this single lollipop diagram, P1 goes to P2, implies nothing goes to P2 at a rate that depends on P1, and then that P2 decays. And so why don't we just review quickly as a little exercise, everybody to get started, reminding ourselves Hill functions. Let's take our diagram, P1 goes to P2. Assume that you have a Hill function for V1, first order decay for V2. Write the rate laws for V1 and V2. Then write the ODEs for P1 and P2. And then solve the steady state P2 as a function of the value of P1. And if that's not a clear exercise, then please let me speak up and I'll do my best to clarify. And if people get ahead of the game and you want to be ambitious, you could ask the question, if I include a step which has messenger RNA, so you have transcription and then translation as separate steps, what do the rate laws and ODEs look like? We're typically not going to use that, but I noted, for example, when I was reviewing the paper that Peter was working with, they did that explicitly. And so that's something that you do see in the literature.
There's
Sure.
a few pieces of information that make me unsure how to write this out exactly. So for starters, it doesn't say whether P1 has a rate of decay, but we can assume that, I guess. It also doesn't say if there's a kind of basal rate of activation when we're thinking about the Hill function. And then there's stuff like the exponent of the Hill function too. So
those are all great questions, and they're all not shown in P1 and activates P2. There are a couple of good responses to that. One, generally, if P1 goes to P2 and it doesn't come from anywhere, your assumption is that P1 is a boundary species. The amount is given. And so then it wouldn't decay. If it were going to decay, if you had P1 coming from somewhere, or you had an arrow coming into P1, then you'd have to get rid of it somehow. So then you would assume decay. The reason you have to assume decay for P2 is because P2 is being created. If you don't get rid of it, you'll get different about. In terms of basal rate of production, that is something you could choose.
No.
You either if you want to assume that it's zero, that's all right. If you want to include a basal rate, that's fine too. That's a choice.
Okay. And then for the max rate, is it common practice just to assume it's 1 for our usual scaling?
It's up to you. Again, you could use
Okay.
a parameter Vmax, or you could set it to 1.
Okay.
Those are both legitimate. Just the way K could be set to be 1, 1/2, or just left as K. You could just leave it as a parameter. And then the third thing you asked was,
I think I mentioned that we don't have, I mean, I guess for something like this, we would just use a Hill exponent of 4 plus, right?
I would just, well, for the purpose of this, I would just say that the exponent is H or
H,
N.
okay, okay.
It winds up that solving the steady states is easy, so you don't care. Sometimes the steady states get hard if N is large, but in this case, the steady state's trivial, so it's not.
Okay.
Great questions. But these are exactly the reason that we want to practice this, because this is all missing information that one has to develop an intuition. We could walk through it together. Maybe that's the best way to do it.
Yeah, that'll be best. But for the first one, I could say that the V1 is Vmax times P1 raised to the Hill exponent, let's call it like N, divided by the half maximal concentration, could call it like gamma, raised to N plus P1 to the N.
Okay.
Similarly for V2, I have Vmax negative times P2.
Right. And so what is the ODE? There's only one chemical species, so there's only one ODE.
So that would be the incoming rate, or V1 minus V2.
Right.
And
Perfect.
Connor mentioned you could also add like a Basel rate to that.
So that would add a constant.
That's right.
And then the steady state is simply setting that equal to 0.
Yes, that is where I'm stuck.
Okay. So let's look at this. Here I have a Basel rate. V1, this is the form you proposed, I think, for the Hill function. This is the decay. And so now I add the two together. And that would be my rate. And I set it to 0. And then what I want to do, you'll notice that P2 only shows up in one place. So P2 is equal to B1 plus VM1 P1 to the N over K1 to the N plus P1 to the N divided by KD2. That's it. So that's the full form for the steady state. So maybe it was confusing because it was too simple.
I will say I did it and I was convinced that I had to be doing something wrong. So, yeah.
Sometimes if the problem is too simple, it seems like there's a trick. There's no trick. Okay. And here I've done it out for you. So the ODE here, what I did was I rewrote the variable, the parameters VM and KD in terms of KD. So I'm sorry, B and VM in terms of KD, so that things could scale out. And if you do that, you get P2 star is equal to the Basel rate scaled by the decay constant plus the velocity scaled by the decay constant P1 to the N over K1 to the N plus P1 to the N. And the reason it's convenient to put in this change of parameters is that way, if you change the decay rate, the fixed points don't change. So that's the end of it. This happens to be for N equals 8. This is the curve. So one of the things that I wanted to talk about is the idea that this is like a step function. And I have mixed feelings about using this Boolean analysis. Sometimes you win with it, sometimes you don't. But sometimes it helps you develop intuition for complex circuits. And so if I imagine my Hill exponent getting to be very large, then if P1 is less than K1, P2 star is 0, or the Basel rate of transcription. And if P1 is bigger than K1, then I get my maximal rate of transcription. Something like this, a step function. And if we're used to doing logic analysis, because we do logic or we do computing, then we tend to be more comfortable or familiar with doing AND and OR gates than we do with the mathematics, so therefore it may be for some people an easier way of dealing with this. And so we can imagine that there's an abstraction of this Hill function, which is just if P1 is less than K1, we have a low value. If P1 is bigger than K1, we have a high value. So now let's do the other one. Having done the first one, maybe it'll be easier to do the second one. Why doesn't everybody do the first one, the second one, which is just do the same thing with a decreasing Hill function? And not very much changes. So I hope that having seen that first one now, the second one is easier. And maybe it'll help if I go back and show you the result for the increasing Hill function.
If we use the same process as before, but now we're working with an inhibitory Hill function. So we have our half maximal expression term, the Hill coefficient in the numerator, the denominator, plus the P1 to the Hill coefficient in the denominator, and then the process carries out the same otherwise.
That's right. The only thing that changes is the P1 in the numerator turns into a K1. Everything else carries over. So if we do this here by steps, V1, we have a decreasing Hill function here. I've included Basel transcription again. First order decay, step 1. Here I've done that rescaling, although you don't need to do that, so that it comes out nicely with the decay. I add the two together, C1 KD1 2, the Basel transcription, plus the decreasing Hill function minus KD2 P2. I set the left-hand side to 0, solve for P2, and all I have to do that is move it to the other side and divide by KD2. And you see why I put the KD2 is because then the KD2 cancels out everywhere. When I write it. So I get this. P2 star is C1 plus K1, K1 to the N over K1 to the N plus P1 to the N, decreasing. Max value is C1 plus K1, min value is C1. Inflection point, half maximal value is at K1. If I happen to set K1 equal to a half, then everything is scaled in an easy way. Don't happen. As before, I can imagine this as a step function. If P1 is less than K1, I have a high value of P2 star. If P1 is bigger than K1, I have a low value of P2 star. So summarizing, P1 goes to P2, you get that fixed point, increasing Hill function fixed point. Go decreasing, you get a decreasing Hill function fixed point. Notice that the value of the fixed point has exactly the same form as the value of the rate constant. That's only true for these simple one component networks. If I have something more complicated, the fixed points will be more complicated. And so I can imagine 0 to 1 for the increase, 1 to 0 for the decrease. Okay. So now I'm going to do, we've done one step. Now we've got to cascade these together. Suppose P1 turns on P2, P2 turns on P3. I want to know what happens between P1 and P3. The Boolean approach that I'm suggesting people think about only works if the K's are the same for everything. If the capital K's are the same. If you're doing logic circuits, if it's TTL logic, everything is 5 volts. If it's CMOS in the old days, everything was 12 volts. You can't plug in a 5-volt circuit into a 12-volt circuit. It doesn't work. And so if the K's are different, then the scaling is different and things aren't going to behave. And so this logic approach really only works if I assume everything has the same order of magnitude and amplitude. So let's imagine P1 turns on P2, P2 turns on P3. And let's just think about it this way as a logic gate. Suppose that P1 is less than K1. Then P2 star is 0. 0 is definitely less than K2, which means that P3 is 0. If P1 is bigger than K1, P2 star is 1. 1 is bigger than K2, which means that P3 star is 1. So the logic is if P1 is 0, P2 is 0, which means P3 is 0. If P1 is 1, P2 is 1, which means P3 is 1. So that's the Boolean interpretation of this. And so the net effect is you might as well just have said P1 activates P3, because if P1 activates P2 and then P2 activates P3, the final fixed points are the same. The temporal behavior will be different. And here you could see what would happen with K1. Suppose that the output of P2 star were small. Suppose even when P2 is turned on, its value is less than K2. Then no matter what I do with P1, I never turn on P3. Similarly, suppose the basal rate of production of P2 were bigger than K2. Then this minimum would push me to the right-hand side of K2, and P3 would always be turned on no matter what the value of P1. And so that's what I'm saying about you have to think about the values being compatible with each other for this analysis to work. And to some extent, I think it means that I don't know always how useful that analysis is. If people are used to computer science, then it feels natural. If you're not, then I don't know how useful that analysis is. Maybe easier just to do the math directly. Okay. So again, coming through this, we have P1 activates P2, P2 activates P3. We assume that P1 turns on P2. If P1 is too small, P2 doesn't turn on. If P2 is off, then P3 is off. So the net effect is that P1 turns on P3. All right, so why don't we have people do this? Sorry, Joel, go ahead.
Yeah, I have a question. How do you do if you want to cut the middleman in that case, and how do you define a new K? Let's call it K3, that is the sum of K1 and K2 in that case, if you want to cut off the P2.
I'm sorry, I'm not sure.
So if the net effect of P1 activating P2 that activates P3 can be summarized as P1 activating P3. How we define a K that is the combination of the two Ks beforehand, so, or the P1 or the K1 and K2 is just a sum.
Good question. If K1 equals K2, then the K for the whole thing is that K.
Right. If it, oh,
If-
but, okay, we are assuming it, they are equal, okay.
Right, if K1 is less than K2, then it gets to be a little bit trickier, but in general, it's the small, depending on whether it's activating or inhibiting. If it's activating, it's the smaller of the two Ks. If it's inhibiting, it's the larger of the two Ks. I
Oh.
think you better check that. So here, this is the next assignment. So I originally was going to ask people to do all of them, but I'm not. I'd like people to group. I'll do a little break. I set up some breakout rooms. I'd like the first breakout room to do P1 inhibits P2 inhibits P3. I'd like the second breakout room to do P1 it activates P2 inhibits P3. And the third breakout room to do P1 it inhibits P2 activates P3. And I'd like you to do the little logical analysis of these. And I'll give everybody 5 minutes. How's that? Something that people suggest, I suggested I mention, which people may have figured out on their own, is that in the breakout room, you could use the screen share to do a whiteboard. And on the whiteboard, everyone can draw on the same whiteboard. So you can have a shared notepad place to doodle and draw that everybody can write on together, and you can save the value, you could save the whiteboard. So that can be a way to work together, even if you're not physically in the same room. If people have any issues with that, let me know and I'll show you how to do it. So would people from the inhibit group like to tell me what you got? If you want to screen share, that's fine. Or if you just want to talk, that's fine too.
We didn't really produce a visual aid, but in words, basically we got an activation with a threshold of K1. Because if P1 is greater than K1, then the value of P2 will be 0. And if the value of P2 is 0, then the value of P3 will be 1. So
That's fine. It's not, as I say, sometimes these things seem harder than they are because they're too simple. So that's great. Okay. How about the activate inhibit people?
Kind of a little bit of an inverse of that. So we have a threshold K. If P1 is below K, you get no activation of P2 and therefore no inhibition of P3. So you could say low P1 activates P3. Conversely, if you have high P1, you get activation of P2, which gives you inhibition of P3. So P1 inhibits P3.
Perfect. And then inhibit activate. Supriya, maybe? Somebody from Gabriel, Joel, Peter.
Yep. So P1 and the summary is P1 inhibiting P3, because if you have the presence of P1, that means that there is no P2 or an inhibition of P2, which activates P3. So it's the same as saying that P1 inhibits P3.
Right. So the activate, inhibit, and inhibit activate for steady states do the same thing. And inhibit does the same thing as activate and activate for the same same steady states. Now temporally behaviors are rather different, but the steady states are the same. Okay, great. So everybody got through that just fine. So we can get through those. And there's a little summary of it. And now we want to talk about the time behavior. And the time behavior is a little bit different because what we care about is when does P2 cross the K for P2 to P3. P1 is a fixed value, so we don't have a time behavior, but P2 is changing in time. And so what we'll see is if we turn P1 on, P2 will increase. So P3 will start at 0, and then at some point, P2 will come up above K2 and turn on P3. Similarly with this one, if we start off with P1 0 and turn it on, P2 initially will be turned on, and then at some point it will turn off, and that will turn on P3. And so the temporal behavior is a little more complicated than the fixed point behavior. And in that case, it really matters what the time constants for these things are, and also what the values of K are, because the speeds are going to change. And so when we go to that, we're going to have to actually do some solving of math, not just do the logic. Joel.
For the second case, I think we also have to assume that the production of P3 comes from somewhere else, or if the P3 is already existing in the system, right? Otherwise, you'll never leave 0.
So you have to think about what the initial values are. That's right.
Right.
You have to say, is it you assume that P3 is initially turned on, turned off? Where do you start?
Yeah, it has to be different than 0, otherwise you don't get any change, right? Okay.
Okay, so now let's think about time dependence. And let's just start out with our friend P1 activates P2. And we wrote the OD, dP1 dP2 dt was equal to a Hill function minus K2 KD2 P2. Notice that this Hill function is independent of P2. So this looks complicated, but it's just a number, just a constant. And so this differential equation is dP2 by dt is equal to a constant minus KD2 P2. In other words, it's an exponential. So this may look complicated, but it is just exponential relaxation of P2 to the fixed point. Now, what we're going to care about is when P2 crosses the threshold K2 for the second circuit. And so what we're going to want to know is if we have this as our time series and we draw a line across it at K2, how long does it take to get from 0 up to that value? Which is, I think, Joel, what you were getting at. And that takes a little bit of algebra. And in the slide deck, I go through all of that algebra. And I'm not going to drag you through the algebra today. But if you ask the question here, I start out with P2 0. I turn on P1. P2 begins to come up. I know its equilibrated value. I know its steady state value. That's given by that Hill form. And the rate at which it increases is going to depend on K1, the rate of increase. The top final value is going to depend on K1 and capital K1. And so the time it's going to take to get from 0 up to crossing K2 will be a function of K2 and K1 and KD2 and everything else. If I invert this by hand, and as I say, it takes a little bit of algebra, it's not terrible, I find that the time to get to a value of K2 has the following form. It's 1 over KD2, that's the decay rate. And that maybe seems a little bit, actually it makes sense, I guess. If the decay rate is fast, actually maybe not. I would think that if the decay rate is fast, the equilibration time would be longer. And so this looks a little bit contradictory. The reason it looks that way is because the decay rate also factors into the fixed point. And so that's a little bit and here I've reduced it. So it's 1 over KD2 times the logarithm of P2 star minus the initial value of P2 divided by P2 star minus that fixed point K2. And again, the algebra is not terrible, but I don't want to take the time now to do that derivation. If you assume that your initial value is 0, then you lose that extra term in the numerator, and you can divide through by P2 star, and you're left with 1 divided by KD2 logarithm of 1 minus K2 over P2 star. And the question is, how does that time depend on P1 and K1 or K2? So let's do a little exercise. Fire up antimony, please. Tellurium on NanoHub. And to begin with, you could simply write something that gives you the time series for my Hill function form. And then you can ask the question, how long does it take to get to value K2? What I'd like you to do then is scan that time as a function of P1, and you'll have to repeat it for different values of K2. Is that clear? And if you get stuck, I have it worked out, and I sent a link to the notebooks if people need them. But I'd like people to take a few minutes to try it out. Would people like to do that on their own, or do you think this is something that, again, would be good to do in small groups?
I'm always up for groups.
Okay.
Same here.
Groups.
Okay, how many? I think 4 people per group was too many. How big should the groups be?
I liked it at 4 personally.
Okay. I don't have a problem with that. I'll create 3 rooms. I'll just call them group 1, group 2, group 3. I'll create 4 rooms, group 4. And I'll open the rooms and I'll let people self-assort to the rooms. And so you could decide how many rooms you want to do. And I'll give you, this one probably takes a few minutes more. So I'll say maybe, let's say 8 minutes to try to do it. And if people are stuck, come back and let me know. So this one was this was, I think, Juliana, the one you said I should assign as an exercise, because I was just going to show them the result. No, Hayden, you were the one who said to assign it as an exercise.
Sorry, I stepped away for a second there. What was the?
I originally had this, so I was just going to show the result, and you suggested I make it an exercise.
Mhm.
So we'll see how it goes.
Yeah, I thought it might be good to have them doing a little bit more in the early parts of this lecture. Seems like they're enjoying working in groups at least.
Mm-hmm.
Well, and I think if they were, again, I feel so awkward about putting this in the recording. I think that if it was if they were having to work as hard as they did for the things that we were doing, then it's important to do it. If everybody had come back with that first assignment in 30 seconds, I would have said we didn't need the exercise. But the fact that it took people some time means that it was important to do it.
Mhm.
Yep.
And this one actually does require a little bit of Python. Because you get the time series and then you have to find the time at which something happens.
Right.
Yeah.
And I don't know if you're in the breakout room, can they see this share screen? Or do they
No.
lose it?
No, they lose it.
So then I'm not sure how
Well, they could be on YouTube. Hi, people. Watching 2 minutes ago or something.
that would work.
Hey,
Joel,
James.
what's up?
Question about what is the circuit that we're working on? Is activation? Is it
No,
activation
just
inhibition?
one. No, just activate.
Activate.
No, just activate.
Just
It says
one.
P1 activates P2.
Oh,
That's it.
okay.
Let
got
me good
confused.
point. Let me say that to everybody. Joel has asked a great question, which is the circuit is the one we started with, which is the simplest possible circuit. P1 activates P2. So all you're doing is saying P1 turns on P2, and you want to know, given P1 goes from 0 to 1, P2 is initially 0, how long does P2 take to get to a value of K2? That's the assignment, assuming a Hill function activation.
So for the activation of P1 to P2, we have a K1, right, value on the Hill function. But you're asking about a K2, which might indicate that needs a third species, right? Or
No.
if we just
No.
put it in a.
It's just when does P2 get to the value of K2?
So we can establish that value of K2.
That's right. K2 is a parameter. You just want to know how long does it take to get to K2.
Gotcha. Okay. Yeah.
If K2 is very large, it never gets there. If
Makes
K2
sense.
were 0, it's there instantly. So it's just I could have just called it A instead of K2. But
Yeah.
I happen to know that it's going to be K2
Going to be
later on.
connected on the other equation.
Right,
Yeah, for
that's
the
right.
activation of the P3. Yeah.
That's right.
That's why we got confused too, because it was like, wait, K2 just only appear on the next one. We don't have any K2 when we were, writing it out.
Right.
But okay.
How'd it go?
I think we made progress. Time will tell whether we made progress in a way that looks correct.
Well, I just embarrassingly noticed that it looks like I managed to overwrite the code that I said was the one you should use. And so the online code that I have isn't the right code. So it's mostly right, but not quite. Well, let's see. Guess I can. Well, why don't we'll talk it. The results on the screen are the results. I had meant to share the code, but as I say, that looks like I clobbered the file. So, sorry. All right. Well, let's pull people back and see how we're doing. So how did it go for people?
We did not covary P1 and K2 and time. All I did was find the time to reach the threshold as the threshold changed, given a fixed P1 and K1. Or yes, yeah.
That's fine. But This one is work. Because you first have to create the time series. Then you have to figure out how to calculate when you get to some target value. And then you have to figure out a way to do the parameter scans and stack it to display it. So maybe it's a better homework problem than it is a in-class problem. How did people do? Did people make some progress on it? How far did people get with it? And did talking with each other help or not?
Talking with people definitely helped, I think, at least for our group, which was Danusha, Lindsay, Zach, and I. We ended up sharing screen and
Good.
kind of going through code together. We did not, as Lindsay already said, we did not quite get this, but we did manage to explore some and make some sense of it, I think. Part of it was also, we did poke the code online as a kind of like check to see how we were doing, and got a little bit confused by the by that, but besides that, I think we were good.
So did anybody make other progress at the other groups? How to go for the other groups?
We were pretty similar. It was the same thing, plotting everything except the P1 and K2 co-varying. I think that was just the part that I know we were all kind of grinding at. Yeah, that's basically it.
Yeah, V-stacking things always takes time to build those arrays. What I tried to do is I have some code that does a parameter scan, and then I try to keep that available for myself. And so then if I need to do a parameter scan, I'll reuse the code rather than try to reinvent it.
Joel and Peter were almost there. I don't know if they ended up finalizing it, but I did not get there.
It's as you say.
Yeah, yeah.
Joel, do you have?
Yeah,
Not
it's unfinished, but if you want, I can share. Let me put in a different screen here because on my vertical screen, it doesn't look as nice. So give me a second. Let me do some. Okay. Sure. Yeah, I don't know why, but the K2 line is just like this small, although I'm using the length of time as a plotting function, but I don't know, something is not right. So yeah, Pete did this great job of like using P2 here for us to starting with P2 to change the P2 we see what are the values. So basically, yeah, when it's equal, when P2 is equal to K2 is the border threshold for it to activate K2 in this case, right? So we can do the same thing but for other parameters too. So just copy this and do multiple times, I guess. And we change instead. Oh, this is for P1 actually.
Yeah, you wouldn't want.
Yeah.
Well, P2 doesn't change. P2 is the result.
Right. So we can change this for K1 and then we just call it K1. Let's see if that works. Live testing. Yeah, that also do the same thing.
Right.
Anyway,
Yeah,
but we
so
got
so-
the.
So here you see that the time it crosses that line will change depending on the value. So you do see that the time changes.
Right. And we can
So-
also change the value of K2 as one of the things you mentioned.
But so then the next thing you'd have to do is find out at what time do you cross that target value.
Making probably the time smaller is a good idea to start, and then yeah.
Is
And
the
that-
reason? Oh, sorry.
Go ahead. Go ahead, Connor.
No, I was just trying to think of why your line was cutting off, and I was gonna say, when you say length of time, right? Because there's two things. There's the actual duration that we're running it, and then there's how many times we're subdividing it, which is the actual length of the array. So the mismatch there could be why it's not stretching all the way.
So if I do times 200, let's see. Nope. Yeah, it's something catchy here, or let me see. Oh, okay, this, nope. Yeah, I don't know either. It's not worth.
Well, the Y value is not something you're rescaling. It's the time that's got to be rescaled. It's the X value. It's time. that has to be
It's true.
bigger.
Yeah, then I lost everything. Yeah, because
Because it's not 200, you have to
20.
determine what the conversion.
Oh, yes, okay. Yeah, it's going.
So this one, I agree, is a little bit tricky, and
Oh, it is.
there is code for it. That it's not the most elegant, but it is available. Let me come back to that for a second here. Let's see. Where did my all right, why do I not have and we can come back to the code, I guess, later. What I wanted to just show you though is the result, which is, let's just look at this time series here. If K2 is bigger, then it takes longer to get to your target. Clearly, if K2 is bigger than P2 star, you never get there. So as K2 gets large, in principle, the time gets infinite. And so what you see, if you ask how long does it take to get there, is if K2 is small, K2 here equals 1, then the time to get to K2 is more or less independent of P1. As K2 gets smaller, the time gets longer for small values of P1. And so if K2 is here 0.7, let's see, actually the color maps right. You know, K2, here, sorry, I got backwards here. K1 is 0.1, it's basically independent of P1. As K2 gets bigger, I'm pushing up further and further, I get more and more sensitive. It takes longer and longer for small values of P1. And that's something we can play with. Again, this is the program that does it is this Hill time series convergence times V0. So now, and I originally hadn't planned on doing that as an exercise. So maybe it was a mistake. Maybe I should just have shown the result. What I would like people to do is now actually do the stack. And I'm not going to ask you, well, the third one actually does ask you to do this, but let's try this now together. Write the circuit, P1 turns on P2, P2 turns on P3. And let's assume that all the Ks are 0.5, make life easy for ourselves to begin with. Let's the rate constant C1 be 0, CK1 be 1. And then let's run that simulation. What we're going to see, and there is one here, feed forward coherent events is the simulation. Here, I have started out with P1 to 0 for a little bit. I turn on P1, that's this red line, this blue line. When I turn on P1, P2 immediately starts coming up. So that's this orange line. But P2 doesn't start doing anything. P3 doesn't start doing anything until P2 has crossed the value of K2. And so what I see is that there's a delay in P3. Does that make sense to people? So I turn on P1, P2 starts coming up. I have to wait until P2 gets to the value of K2. And at that point, P3 starts coming up. And it takes some amount of time for P3 to get to its threshold in case there was something further downstream. And so I see a delay. And so why don't people try doing that? If you have code that runs the 1, you can easily copy that code and feed P2 into the same circuit again to create P3 and plot P2 versus time and P3 versus time. So just try to replicate this picture here on the right. Don't worry for the moment about doing a parameter scan. Just plot the time series. Is that okay? And why don't people stay in the main room and do it? We'll all do it together. And then here it asks you, and I keep saying a fixed value of P2. What it should say is a fixed value of P1 instead of P2. Plot the dependence of this time on the value of K2. What you'll see here is that if I make K2 bigger, it takes longer and longer for P2 to reach K2, which means it takes longer and longer for P3 to start turning on. If K2 is in this region here, moving K2 doesn't change the time very much. If I push K2 up to near P2 star, then small changes in K2 make a big change in the time. And that's something that people can look at even if you don't do a formal parameters. So let's give that a try. Take your circuit that did P1 goes to P2, plug P2 into P3, plot the time series.
I am having a little trouble trying to figure out how functionally to make it to determine when a particular like when one of the P's reaches a particular value, how to do that.
Okay, that's actually that was one where I hoped having people in breakout rooms would work. That was why the main reason I was hoping people would join the breakout rooms would get to that point. So let's look at this together. Let's look at this together. And let's do some hive mind. So what do I have here? I have P2 being created, P2 being destroyed, P3 being created by P2, P3 being destroyed. And here I am simulating it, and I turn on P1 at time 1 so that it starts at 0 and I can see it turn on. And I have multiple plots, but in fact, I don't really need the other plots. I only need the first one. So I can comment these out. And I get that, which is what we had on the screen. And I can put this in the chat, code in the chat, if people want. Now, the output of this is in MM. So if I look at M, let's print M. And see what that looks like. M is a NumPy array with the columns labeled. And so if I want to find out, what I want to know is what time, first column, okay. I want to know what time the first column reaches, the second column reaches the value. So there are a couple of ways I could do this. I could do it in a sort of a Fortran-y way, which is I could iterate through the indexes, find when the value in P2 gets above some threshold, and then read out the time index there. And that will work. And it'll give me what I want. I could also, this was sort of, I was hoping that the people who are Pythonic would do this. There is a NumPy function that will return the value in column X at which point the value in column Y reaches something. And so I would encourage people to do a little bit of Googling into NumPy or Stack Overflow and find out what that function is. Now, the reason that I had these additional lines here, which here I'm plotting P1, P2, and P3 all on one plot. Later on, I was doing them one at a time versus P1, time versus P2, time versus P3. And the reason I was doing that is it's a little bit easier to use that NumPy function in the 2-column array rather than to have to tell it which columns to use when you're doing that. So why don't people look up a little bit? Why don't people try doing this? You could say, okay, my target value is, pick a value of K2. And the value of K2 is going to have to be, if I look at my values, it has to be between 0 and 1. If it's bigger than 1, you never get there. So pick a value K2 between 0 and 1. I'd ask the question, at what time does P2 get to 1/2? And print that value. Okay? Does that make sense? And I can iterate. I could iterate over the first column. So I could say for I in array and do it that way. That would work. I could iterate over pairs. I could say for I comma j in the 2-column array. That would work. Or I could look up the NumPy function that actually returns the line where the value is the target.
Sorry, but cannot you do like a np-argmax to return the index of a specific thing that you're looking?
Mm-hmm.
Okay.
Yep. I
Isn't
use
that easier?
min, but yes.
Okay.
There are a lot of different ways to do this. And if you have one that you like and you want to show it, by all means, just share the code and show it. And we'll all try to do it. People able to use where to make that work? I did it by hand and walked through index by index, but that's not a very Pythonic way to do it. I'd be happy to see somebody else's suggestion.
Yeah, I can share my screen.
Great. Let's see.
Yeah. Here we go. Share. All right. So this is just what I did. Not sure if it was very easy once I learned that thing. Because basically all it does is it just looks at P1, sees if it's greater than or equal to 0.5. And then normally it returns an array of every single instance of that. So I just returned the very first instance of that. And that's it.
So let's see what it gives you a array, it gives you a row number, is that right? Or you're actually.
It gives
is
you
that
the index.
Is that the time?
Yeah.
Like so then you
Oh,
want
that's
to
not the
look
time,
up,
you're
then
right.
you want to look up the time. You want to look
Yeah.
up,
So I'd have
you
to
want to look
do,
up column 0 with that index.
right, I'd have
The
to
readable
do,
time.
what is it? Trying to think, it'd be
Well, it'll be outside the where.
time.
It'll be outside the where returns the index.
Oh, right,
So
you're
now
right.
you want to pass that to the array.
Yes, so it would be time,
Right, there you go.
and then, and I get to the end. There we go.
Yeah.
There we go. Okay. So that's the times that it came back with, which are a little weird looking, but I think that's because it's a rounding error.
Because there's a finite increment, right? We're not going to continue, right? There's a fixed time, there's a finite time step.
Yeah.
So it's not going to be perfect. Great, that works. So now you could do it. So now you could change the value of K. Now you could, that 0.5, you could now scan that. You don't actually have to regenerate M, because once you have the array, it's there. You're using the same array. So now you could wrap that print statement in something where instead of 0.5, you scan K from 0 to 1 with an A range. And then plot the value.
One interesting
From
thing.
0 to 1. Okay, so like a lens space then?
You could do that, or I like N pi A range.
I see. And then you just do, I don't know, like 10.
That
And
works.
then you just would do something like,
Instead of 0.5, it would be.
yeah. And then probably would want to do something like for I equal, or for K equals I.
Right.
And I have to make sure to have a T because that's how you spell print. There we go. So yeah, okay. Cool. And then it just has them all outputted.
Right.
Different ones. It's not very pretty, but I'm sure
Right,
I could plot it. It'd be
Right,
nicer.
you could create an array and VStack it if you wanted to.
That too. Yeah.
Why don't we do that together? Why don't we create an empty array?
What, with my screen shared or?
Yeah, you could do that. Great. And then you could
Okay.
share the code with everybody. So
Okay,
do a little-
sure. So, yeah. And the length of it would be, I'm trying to remember how this works. It's like
I usually use NumPy empty.
empty. Okay. And then it would need to be a 3 by 10 array. So is that
Or you could make it 3 by 0.
3 by 0?
Actually, you need it to be 4 by 0 because the first column is
Oh, I see.
the ordinate.
Like that?
It's square brackets.
Okay.
I always have to look up empty. If somebody, this is why I say hive bind is useful, because usually there's somebody in the room who's a NumPy expert. So I remember.
I've never fully committed it to memory. So there's a lot of NumPy stuff that I'm still learning. And then it's it would be bar dot
That would be an append.
It would be an append, but it would be,
And then
It
you need to
have to-
cluster them. You need to have, the first one would be I, and then the others would be those values that are there sequential.
oh, I see. So it'd be something like this, and then if I get that right, something's wrong with what I did.
Well, I would say I would append, you're going to append a list. And the list would consist of the first element is I. The second one would be that first thing that's in your code. The second one would be the second, the third, it'd be long, it's gonna be a long line.
Oh, I see what I did wrong. Okay. I had to put it inside of this. Whoa.
Or
Sorry,
if
my
you
cat
wanted, you could,
is-
or if you wanted, you could calculate the time separately and then do the append after you've calculated it.
But I would just basically append it to each one and then just set each one to a different value.
Well, so what I think you want, I think should let you guys figure this out for yourself. The way I would do it is I would have the first column be the value of I, or value of K. The second one would be the time at which P1 reaches K. The third one would be the time at which P2 reaches K. The fourth one would be the time at which P3 reaches K.
Is this the right formatting then?
Well, so
I feel like I'm doing something wrong.
So set, just set, instead of doing an append now, just create a variable for each one of those three lines that you have in the append.
Okay.
Create the first one being time P1, the second time P2, and the third one time P3. But I should let you guys figure this out. I shouldn't be telling you. So I'd say time P1 equals P1. No, it's okay, fine. Okay, and now you could do your append, which would be appending square bracket I comma, there you go. I got it all.
Yeah, just GitHub Copilot just knew what I wanted.
Yeah, there you go. And then you can do a plot array on the final result for the array.
And then I just do, I think it's like TE plot array, right?
Yeah, plot array with capital
And
A.
there we go. Let's see if that works. It did not like that. ND object has no.
Okay, so you'll have to do a VStack.
Okay.
So it'd be array equals, instead of append, it would be array equals numpy.vstack parenthesis
Mhm.
and then array comma and then that.
Array
No, just ARR comma. No, just.
Oh, I see. Like that.
Yeah, I think that's right, isn't that? Yeah.
Takes one positional argument, but there are two given.
All right, somebody has to.
So I think
There's probably a parenthesis missing.
let me see what VStack does. See VStack sequence. So it takes an array like tuple
Yeah.
into it, and then it just outputs that. Well, then,
I think.
oh, is it this? Oh, I
Yes,
think-
yeah.
Yeah, it's an extra.
that's it.
Yeah, that's an extra square bracket. Yeah.
And now there's another thing. All input dimensions.
Oh, because when you created the array, I think it's backwards. I think your initial array has to be 0,4.
Okay. Almost there. Index out of bounds for axis 0 with size 0. Okay. Now what's going on?
All right.
Index is out of bounds.
Maybe it was 4.
Hmm.
Let's look up empty.
Let's see what the It's for P2, so if I try doing,
I think for empty you need 1,4.
Oh, it's, yeah, sorry, it's, no? Okay, try that.
okay. Yeah, that's still giving me the same issue. I think it's probably
Where
has
is
to
it,
do
where is
with
it drawing the error?
this. Let's try seeing what happens if I print it. Okay, no, it has, it's an array, so it should have a, oh, so one of them is empty for some reason, because it goes out of bounds. So, but why is it going out of bounds?
Maybe if for some k it never
Don't start at zero,
crosses-
don't start K at 0, start K at some
Yes.
finite value.
Oh, don't start the loop at 0, started at
Yeah.
like 1 instead, and then
Yeah.
or no, probably
Point
point.
one.
Let's just do 0.1, yeah.
Fine.
That's still, yeah, see, so the issue is that I think it's going, so the M value for P2. Oh, you know what it is? It's that at one point, I don't think it goes above the value.
Oh, so
Right,
one is the problem.
It doesn't hit 1.
High.
Yeah, so if we do 0.9 instead, then this should work. And I think that this needs to be 0 again, just in case. Yep.
Yeah.
That looks
Not
like,
real pretty, not real pretty, but you're getting there.
yeah, and you can increase, you might be able to increase the lens space to do, oh.
Yeah, there we go. That's it.
Yeah. Yeah, so we can just keep increasing this and it'll eventually, or
Yeah, it's
hopefully.
smooth.
It's
Okay,
kind
so
of
good. So now
so
you got the
rugged.
time. So the x-axis is the K value and the y-axis is the time it takes to get there. Now what you see is that P3 turns on after P2. Right? As you change the target. And if you make the target too big, it fails, which is what you saw. And if you wanted to be found, you could label the axes now. Right? You could label the x-axis K2 and the y-axis time.
Right, and that would be in,
The plot array.
yeah, it's I forget what the value is legend? No. I forget what the show labels, is that it? I don't remember what it is.
Doesn't, I mean, I don't think, why don't we share the code with people and everybody
Yeah.
can try?
Sounds good.
Thank you for being a guinea pig.
No problem.
And people may come up with different solutions. It's a nice one. And I'll give everybody a minute to run it. Make sure they run. Because that's a good method to have. You may want to use it elsewhere.
Did
I mean, it's
people
not
get
very.
it?
Did it work for people?
I'm wondering if people got in the chat. I
It's
think
in
I
the
sent-
chat. It just takes
Yeah.
a moment to copy and paste it and make sure that Zoom hasn't butchered the formatting.
Yeah, yeah.
Thank you, Zachary. It was very nice of you to do.
No problem.
Zach, I'm always impressed by your ability to live debug. You're better at it than most people that I know, certainly better than I am at it.
Yeah, especially since I don't really remember like half of NumPy at any moment in time. I have to like Google the majority of the the majority of the methods. Yeah, I don't know what it is. It just doesn't seem to be intuitive to me, even though it's like the most efficient means of doing most coding in Python.
Yeah, well, slicing is never very intuitive, I think. And exactly what the bracketing has to be is also not always intuitive. When everything is like the fact that you have to put things that make a list of the list. That's an example.
Yeah, that's the big thing for me is that with the way Python does it is like standard practice across most code, like most coding languages, the way that it's done. And that makes sense to me. Like I can understand it. But for some reason, the way that NumPy does it, I think it's because they're trying to appease mathematicians a little. And so that just completely breaks my brain every time.
Okay, did people get it to run? Did everybody get it to run?
Yeah, it runs
Does
great.
anybody need more time on that? Save it, so you've got it for future reference, because for the homework, you'll need it. Okay, great, thank you. Okay. So let me move on. There's something else that we need to do that I think is important for today. And I want to, I'd like to come. I want to come back to something, which is if we're going to do the feed forward array, we have the direct path and the indirect path, which means that we have both P1 and P2 modulating P3 at the same time. And so we have to decide how those signals combine. And there is no universal way of doing that. That's going to be a biological question, fundamentally, and a mathematical question. We could, normally we will assume that either combination works like an AND gate or like an OR gate. But potentially it could be something more complicated. And so here we have, remember in our feed forward network, we have P1 coming into P3 and we have P2 coming into P3 at the same time. How does P3 change as a function of P1 and P2? And so again, the main idea is that we're going to assume either an AND-like structure or an OR-like structure. However, sometimes the interactions are complicated. And when they are, and you're stuck. And in one of Herbert's textbooks on control theory, he gives you a whole bunch of different zoology of possible combinations. And there are a lot of empirical ones that are what's observed experimental. In our world, we're just going to assume that P1 and P2 both come into our gene and affect the rate of transcription of P3. And we'll assume if it's that they're both activators to begin with. And so what would it mean to say that P1 and P2 modulate P3? That's not a trick question. That may be one of these questions that's too simple.
Means that both are needed to activate P3.
Right. And if I have P1 or P2 activating P3?
Just one or the other.
One or the other, okay. Okay, so that as a statement, that's clear. Mathematically, I have to think about what functional form of rate law would give me that. And I realize we didn't get our break, but today we're not going to have a break. We had our break, was our breakout. If I break now, no one will come back. We only got half. So we have to think now about this. We have the concept of a Hill function. Now that Hill function could be a function of P1 or P2 or P1 plus P2 or P1 times P2 or P1 over P2. Or it could be something like P1 to the n plus P2 to the n or P1 to the n times P2 to the n. A lot of possibilities. Here are the rules that we want. For an AND gate, we want our output to be bigger than a half only if both x1 and x2 are bigger than a half. If x1 is 1, we should get our Hill function of x2 and vice versa. As if one of them is turned on completely, the other one should just behave by itself. If one of them is 0, the output should be 0 no matter what. Those are the logical rules that we need. For OR, we want our output to be bigger than a half if either x1 is bigger than a half or x2 is bigger than a half. If x1 is 0, we should get the Hill function for x2. Shouldn't matter. If x1 is 1, we should always get 1. Does that make sense? I want you to take a minute to think about that because it's easy to say, but it takes a little bit of thought. Don't.
When you say 1, you mean bigger than half in this case? Because if it's 0.6, isn't it 1? Theoretically speaking, or 0.5, whatever. After 0.5, everything should be 1, right? So x1 bigger than 0.5, is that it? Am I getting it wrong?
So if I have the capital K to be 0, I want to be 0.5. My output value will go between 0 and 1. Now, if n is infinite, then I have a step function that goes between 0 and 1. If n is 4 or 8, then I don't step in just a step. I have something that's smooth. And so I do get intermediate values.
So what do you mean by x equal 1 again? I think I got confused there because for me, whatever is the threshold, if the threshold is 0.5.
If my input is 0.6,
Right.
my output is not 1. It's bigger than a half, but it's less than 1.
Oh, okay. It has to be 1. Okay.
Because it's a smooth curve. It's not actually a step function because n is finite. That's why I say it does require some thought. It's not a trivial result. Okay. So as an exercise, and I think this might be a good one to do with the breakout, and people should do this on a whiteboard. Come up with some mathematical form that implements either an and or an or. And I guess the problem here is going to be the same thing as before, which is you're not going to be able to see. I mean, I can do it two ways. I can leave you in the main room and people can work individually, but I think this is something where brainstorming it together would be useful in small groups. So you tell me which is the best way to do it for you. It's just a question I could put the rules. I could put these rules in the chat and then people can copy them, or people could screenshot this. That's probably the best thing to do, is to screenshot this. So everybody has it. I should have suggested that before. That would have been the sensible way to handle this problem. So you have that as a reference. So everybody take a second to screenshot this. Okay. Tell me when you're ready. Anybody need more time? Okay. And so now I want people to break up, and I want group 1. Let's do 4 groups. I want to do people go into 4 groups, so 2 or 3 people in each group, more or less, 2 or 3 people in each group. And I want the first 2 groups to come up with something that's an and. So that obey some function a hill function of x1 and x, or p1 and p2 that has the properties of an and. And I want the other people to come up with something that's got the properties of an or. And I want people to take, we don't have that much time. We get 7 minutes. If you're done sooner than that, that's okay. You can come back. Is that a clear exercise? And then there are a lot of different things that are legitimate for this. And so you should also come up with some little explanation of why you picked the functional form that you did.
I did the absolute difference, found what was the minimum. That's the index. Done.
The problem is that in biological reality, sometimes you'll have 9 signals coming into the same gene, or 20 signals coming into the same gene. And so knowing how they combine, boy, even trying to measure it experimentally is essentially impossible with that many inputs. But what you tend to get, not entirely, but often, are and or. In other words, some of them are required, and if you don't have all of them, nothing happens. A few of them are or, and usually inhibitors tend to be pretty strong. So inhibitors tend to work like and. If any inhibitor is on, it's off. Activators are more finicky.
Right.
Any 2 out of 3.
Yeah. I think I'm remembering right. Nick talked a little bit about that in his presentation when they were here. And I think he had an example of some activation saying that, yeah, it was a combination of or any, or at least 2 on, something like that.
Well, this happens, for example, in the form of drug interactions. Drug A is safe, drug B is safe, but you put them together, it's a disaster.
Yep.
Or sometimes the other way. Drug A is bad, drug B is bad, but you put them together, they're protective.
Yep. They talked about that too. Then there's some, they also showed an example. They couldn't say what drug was it, but was some combination therapy that if you added the 2 drugs together, their power was more than the sum of the parts. But as you kept adding one of them, things reversed and they neutralized each other. It was weird.
Yeah, here we're assuming that it's monotonic.
Yes.
And that's often not the case.
Yep.
It's often what they'd call biphasic, where there's some peak, there's an intermediate level where you get a strong response, and then if you have too much or too little, you get less.
Yep.
Okay, so what did people find, if anything? Anybody want to present some ideas?
Was I the designated writer? Was that what got decided at the last 3 seconds of our Zoom room? Okay. So we did the AND gate, and we had a few different solutions that we came up with. Unfortunately, I wrote them out by hand, so I can do share screen whiteboard if you want me to write them. But
That would be fine.
okay.
Why don't we put up a whiteboard and then Peter can put his ideas up, everybody could put it. Why don't I just create a whiteboard, everybody
sounds
could
good.
write on it.
Mine is a picture.
Oh, well, so Peter, maybe we should do you first, and then I could put the whiteboard up.
Sounds good. So we came up with 2 different approaches, one on the top, one on the bottom. The first one is, since we have an OR gate, we think that you need to translate the hill function into addition. The first way is you could have the whole hill function added up multiple times, and each x could be either x1 or x2. And the second approach is you only modify what's inside x and you put it in parentheses. I think
Go ahead.
Both of these could give similar logic results, but numeric results, perhaps not, if that makes sense.
So they differ in something very important, which is if x1 is 1 and x2 is 1, what is the value outputted from the two? They're both OR type gates, but they differ in a fundamental way.
That appear to be 1 over 0.5 to the n plus 1. And this one, you'd have 2 to the n.
Right. So in one case, suppose x got to be large in both cases. In the first case, if x goes to be very large, I have 1 plus 1, so the output is 2.
This one grows a lot faster on the bottom.
In the second one, the maximum value is always 1. And so in one case, they both have the OR property, but those extra rules that I wrote down that seem sort of finicky about if x1 is 1, the other one should be 0, and so on. The first one violates those, as it happens. Now, I should say that both of them do occur biologically. It's not that what is right or wrong, because both situations do occur, but they are somewhat different. And so if you plotted the output of this as a function of x1 and x2, instead of a 3D plot, you'd see that they have quite different structures. They're both interesting. Great. Does somebody else want to
Before we
that's-
move on, I had a question about this.
Oh, sure. Go ahead.
So let's say x1 is 0.2 and x2 is like 0.4 and the total is 0.6.
Yes.
That seems like it would be, greater than 0.5.
Yeah.
But does the circuit then activate?
So the question here is always going to be the same thing, which is if n is infinite, if n is very large, then the thing behaves like a logic gate. It's a step function. If n is 4 or 8, it's smooth. And so near 1/2, you get a value that's about 1/2. And so 0.6 is just a little bit above 1/2, and so you get intermediate values. If there was a period when people were interested in something called fuzzy logic, which was basically what we're doing here. And it was very fashionable for 5 or 6 years, and then people realized that they'd just been doing null functions and stopped calling it anything fancy. But the analogy between and or is a little bit, again, if it helps your intuition, it's good. But ultimately what matters are the functions. And so writing things to plot those results as a function of the values is I think the best way to do it. You get a sense of that.
That makes sense. Thanks for explaining that.
I mean, I wish I had a magic solution. I have a couple of slides that go over some examples, but and there is, I think I may have one of the demos may actually do the 3D plots. I don't remember if that's included in the set. Does somebody else have something they want to show, or shall I do a whiteboard where we can discuss it with a whiteboard? People should be able to draw on the whiteboard together. Can people write on the whiteboard?
I think you have to enable.
Yeah.
Okay, why is this? Okay, sorry. It's a different, okay. Good old Zoom now has 2 whiteboard creation options, which give different privileges. If you use screen share to create the whiteboard, it's private to the person who created it. If you use whiteboard to create the whiteboard, it's open to everyone. So now you should be able to go.
I draw something as a test. I don't think it's showing anything there.
I've got it. Can people see what I just drew? I just wrote an X.
Yeah,
Okay.
it works.
should I just go? Is that where we're
Go
at?
ahead.
Okay. So
We're almost out of time, so.
sure, I'll write as quickly as I can with a mouse. So the easiest way to do an AND gate that we talked about using the structure we've been doing is just to combine two hill functions scaled between 0 and 1, right? So if you have your x1 to the n over k1 to the n plus x1 to the n. And then you multiply by the same thing, but with x2, you're going to have it be such that they're scaling each other. So the only time it's ever going to be 1 is when both of those are coming out as 1. If one of them comes out as 0, it scales the whole thing to 0. And so on and so forth. I think that's probably the best one out of what we came up with. The other thing we talked about was that you could, in the top of the hill function, you could maybe try something like, oh my goodness, that one. Oh, interesting. If you right click, it goes back to pointer, in case anyone wanted to know that Zoom feature. You could do x1 times x2 in the top and put that to the power of n, and then, you know, complete the hill function. I'm sorry, this is hideous.
That's okay. We can figure it out.
Yeah, but those are probably the top two out of the ones that we discussed in the group.
Yeah, I would say that that's right. I think the and is easier than the or. Because if x's range is between 0 and 1, then multiplication keeps you between 0 and 1. Whereas addition takes you out of the original range.
Yeah.
And so for the or, usually the form that you have on the right, which would be x1 plus x2 to the n over k to the n time plus x1 plus x2 to the n, keeps you within the range. Whereas adding the two separately doesn't. For the and, both of them work. And they do have slightly different structure. If you plot the results, you get slightly different structure. But those are great. I think this was productive. I hope the discussions were productive, because this is definitely a non-trivial. Does anybody else have anything else they want to show before we break for today? I know we have 2 minutes left. Did anybody else come up with any other structures?
It will not let me erase that last dot. Oh, there it goes. Okay.
Now, maybe I'll just show you quickly then what I had as my results, which are basically where we were here. I had the product one here, which is the one you just wrote for the and that does this for n equals 8. Here's x1, here's what you get for x2. And you'll notice that if x2 is small, no matter what you do with x1, it never gets very large. And these intermediate values, everything switches at a half, but you'll notice it doesn't go always to 0 or 1. You get intermediate values. This is actually nice when you plot it in a 3D plot. For OR, there are what are called competitive and non-competitive ORs, which is this difference that Peter was talking about. So here is one, Peter, this was one you proposed, x1 plus x2 to the n over 0.5 plus x1 plus x2 to the n. And that gives you something where the top value is always the same, bottom value is always the same, and the hill function gets moved to the right as you increase. If you increase x1, it shifts the hill function for x2 to the right. Okay. And that one actually is there, and Herbert enzyme kinetics actually use it. This occurs biologically. If either A or B can turn on the gene independently, that works. The other one is x1 to the n plus x2 to the n over 0.5 to the n plus x1 to the n plus x2 to the n. And that one has a slightly different behavior. This is what it looks like here biologically. And in that case, you'll notice the threshold for x1 and x2 is always a half, doesn't shift. The maximum value is always 1. But the minimal value now gets shifted. So in this case, the minimum, the value at 0 for small values of x1 depends on x2. Gets shifted up. For large values of x1, I always get the same thing. Let's see. Probably it would be nice if I could compare these two. They're both ORs, but they have very, very different behaviors. And they both occur biologically. And so I'll leave you with that to think about. x1 plus x2 to the n versus x1 to the n plus x2 to the n. And if you're interested, Herbert has a nice textbook, Enzyme Kinetics, which she goes through lots and lots of different configurations.